Hey everybody, Dr. A here, and in this video we're going to be providing some background information on shear flow. So let's go ahead and get started. It turns out that transverse shear stress, which we call tau, is transmitted longitudinally through the beam's length due to equilibrium. Now, what we call that is shear flow, and we give it a label of lowercase q. So the way we calculate shear flow is quite simple. Q, little q, is going to be equal to V times capital Q over I. Okay, now take a look at this. Does this formula look very familiar? Yeah, I mean, this is the same formula as tau equals VQ over IT, except without the t term, without the little t in the denominator here. Okay, so it turns out shear flow, the way we calculate it, is quite simple, and it's almost the same as transverse shear stress, tau equaling VQ over IT, just no t here, okay? So let's go ahead and consider a beam subject to a shear force V with a rectangular cross-section. Very similar process to what we saw in our other video on shear stress. So you might recall that if you have a side view of a beam here, this is looking at it from the side, what we see is the neutral axis, and then we see this applied shear, or this developed internal shear V, and we have this shear stress distribution here in green. Where is the shear stress distribution the maximum? Well, it's at the neutral axis. And where is it zero? It's at the top and bottom edges. Now, if we looked at a 3D view, again, this should be very familiar if you watched the previous video. If we look at a 3D view, we've got that internal shear force V here, and we have this shear stress distribution in green. We see larger vectors indicating the maximum at the neutral axis, and it's zero, tau is zero at the top and bottom edges, and we have a beam thickness T. Okay, so what happens is it turns out that at any longitudinal line along the length of the beam, that shear stress is going to be transmitted longitudinally like this through the fibers of the beam. Okay? Now, the way we calculate this is little q is V times capital Q over I, all right? And so I can make a little note here. I can say this right here is Q is V times capital Q over I at that particular location, okay? At that particular location without the T. So let's think about this from a 3D perspective, okay? Here's what I'm gonna do. I'm gonna take a little bitty element, a 3D element, from somewhere on the edge of this cross-section of a beam, okay? And so I'm gonna say, let's take a look at this little spot right here and zoom in, okay? If I zoom in and I make it a 3D little view, I'm gonna have a 3D element that looks kind of like this, okay, like a little cube, all right? And so what I'm gonna have here is a shear stress tau, okay, that's like one of these little vectors, all right? Now on the back face of this, I'm gonna have tau going the opposite direction. This is a back face back here, okay? Now, for this little element to be in static equilibrium, I'm gonna need another vector here and another vector on the bottom face, okay? So what happens is by Newton's third law, you're gonna get these vectors that are transmitted longitudinally along the length of the beam. Now, these vectors right here, that's what's showing up, or it's like what's showing up on this top or bottom face, all right? And that's what Q is, all right? So the way you calculate it, again, is the same as tau, but without the thickness T, because we're saying that this is transmitted as a force per unit length flow in the longitudinal direction. So let's make a note here. We're going to say tau had units of force over area, and Q is going to have units of force over length. The force is flowing in the longitudinal direction of the beam, okay? So let's define those terms. We should be familiar with these definitions. V is internal shear force from method of sections or a shear diagram. Q is the first area moment, which is equal to A prime times Y bar prime. And I have a whole video just on Q, okay? That's going to be next. We're going to have a whole video just on Q because Q can be kind of complicated and can be a source of confusion. I is our moment of inertia about the neutral axis. I, we learned in statics. So for a rectangle, you know, I is BH cubed over 12. And if you have a composite shape, you use the parallel axis theorem where you add a plus AD squared. So if you're a little rusty on your moment of inertia, take a look at my statics playlist and see some of those examples, okay? Now, when do we use this? Why do we care about Q? Well, it turns out that shear flow, little q, is commonly used to design connections between beam flanges and webs. So the shear flow, little q, is compared, I spelled compared wrong, let's respell that, is compared to a material strength. All right, so let's think about this. Let's think about this application. Let's say that we have two wooden planks and we want to build them up to a T-section, okay? So if we do that, we're going to have one wooden plank that's going to be a flange like this, and then the other wooden plank is going to be a web, okay? So if you want to build up these two wooden planks, what are you going to do? You're going to lay one on top of the other, and then you're probably going to use glue or a nail, okay? I'm going to say let's look at a nail. So what we'll do is shoot a nail through here, okay? Now, are we going to just put one nail to nail these two planks together? No, we're going to put several nails in there, right? So let's draw a 3D view, okay? Let's say that we've got the flange plank here. And then beneath that, we've got the web plank, like that. And these things are going to be nailed together, okay? So how are we going to nail them together? Well, we're going to shoot a nail through the top flange plank into the web plank, all right? There's the web plank behind that. So we're going to fire these nails into here, okay? And so the question becomes, how many nails do we need, or what spacing of the nails do we need, right? And so in order to figure out how many nails and what spacing you need to nail these two planks together, you need to know information about how this shear stress is flowing through this interface. So that's the shear flow Q that you will end up comparing to a material strength. In the case of a nail, you're comparing it to the material strength of these nails. What if you wanted to glue the planks together? Well, you would perform a similar calculation where you calculate shear flow at this interface, and you would compare that to a glue strength, okay? What if you wanted to weld two steel members together, right? What if you don't have wood? What if you have some kind of metal like steel? Okay, and you need to figure out what kind of welding pattern you need to use. Well, you calculate Q's, VQ over I, V capital Q over I, and then you compare that to a weld strength, and that'll inform you on what kind of weld pattern or what kind of weld thickness you need. okay? So that's why we are concerned with little q. Again, it's to connect elements together for the purposes of a built-up beam. All right, so that's going to conclude this video. We're going to see some numerical examples next of both transverse shear stress, tau, and shear flow, little q. I hope this was helpful to you. If it was, please hit like and subscribe and keep watching these videos so you can best learn this material. Thanks for watching.